Yo, Infinitude Science here, Prachuja Viswas. Thanks for joining in. And I have come back. Yes, it's been a long time, 5 months. A long time has been passed by, and nothing quite of inspirational has happened in these 5 months. But one thing I have inspired that teaching people is my forte that I have come to understand. And so, as always, a long time no videos, so I will be posting some more videos. And starting from where I left last time in chemistry or in physics, you might say in modern physics, uh, I had left over at atomic spectra, and we were discussing about the structure of atom in the oldest theory. And one more thing before I proceed with today's lecture, I would like you to just go to a link in the description, which is infinitude.teachable.com, and that's my new teachable website where I would be posting some new brilliant notes, some quizzes, some various good lectures, some good links, so that you can learn about the structure of atom not just on on the basis of the syllabus of the sophomore or of a high school, but you can also learn about different structure of atoms from various scientists and what were the deep meanings of the structure of atom, like how the atom existed. And if you don't know, like in May 1905, uh, Albert Einstein published a paper which gave the existence of atoms. A lot of people don't know about it, so there will be a small page description on what the paper was all about by me, and it's gonna be really fun. So you go check out infinitudescience.teachable.com. I have also a vast number of teachers coming up together to build courses for you only in chemistry, maths, physics, and if you want, I can get in some more subjects like computer science or whatever you tell me, like psychology, sociology, or some engineering topics, or whatever you like. Right. So let's get on, and just remember that I'm not a teacher, like a teacher in a school. I just want to talk to you all guys about something that intrigues me or intrigues you all. And the most important thing that should intrigue us all is the structure of the fundamental particle of this world, and that is the atom. So we are here discussing about how the atom works and how the atom, if the atom exists, then how do people find it. So that is what we are all talking about here. And one of the most important fact about how the atom came into existence is the atomic spectra. Now we talked about the atomic spectra, and we came upon the formula, a very important Balmer formula or the Rydberg formula, and that Rydberg formula is like somewhat like this 1.09677 into 10 raised to the power 7, and then it is some ni square minus 1 upon some nf square, and then it is meter inverse, and this is equal to some number, or what we call some wave number, right? So it is equal to some wave number. So if I'm not wrong, then let's discuss about wave number, like what is this thing here, like this intriguing thing here. Now by definition, like by definition of physics, I can say, like by the definition of physics, I have seen that the wave number is equal to 1 upon lambda. This is by the definition of physics, but it is a more intriguing definition than the definition of physics. And as an integral definition, I would say that it is, if let's say we have a light source, or let's say this is a photon. I'm assuming that this thing here, this is a photon. Cool. So this is a photon, and this photon has some mu. Okay, like this has become a little more wide. Let's decrease the spectral. Okay, so this is it has a mu which we call the frequency, right? So there are two types of frequencies, like one is called one. If you move into physics, waves and things like that, you'll understand that this one is the angular frequency and one is the normal frequency, right? So because that's in the case of waves and that has been taken from there. So we'll talk about waves one time before moving on, and when we'll discuss about the luminiferous ether and things like that. This is not a part of the structure atom, but it is a very important topic because of Albert Einstein's point of view. So it's like about talking about the luminiferous ether, that there don't exist any luminiferous ether using the Michelson and Morley experiment. So that is something different. And right now we have frequency that denoted by mu, a Greek letter mu, and this photon has a frequency of mu, and when we divide this mu by the speed of that particle, okay, and in this case the speed of that particle is c, so let me just divide mu by c. So this thing here which I have drawn in this blue box, I've written in blue, this thing here is called the wave number. And if you closely look at this, then by definition it comes out to be 1 upon lambda. Now 1 upon lambda means the number of waves that pass through one point in 1 second. So if you draw, like you have this and you have number of waves passing through it, and you select one point here like this, then the number of waves passing through this in 1 second is the wave number, right? So that is the concept of wave number. And this wave number was important because if we talk about the atomic spectra, so let's suppose that we have like this is a plate, we have a glass plate here, okay, and then we have lines. So we start here, like first we have this blue line, then we have the yellow line, and then we have something like we have a green line here, and then we have those red lines somewhere at a distance here, okay. So this spectra that is happening here in this, like this is what we call the spectra, right? So this is the spectra. Am I wrong? No, not like the colors may be wrong, right? But this is what they call the spectra. Like when the light comes and then there is fluorescent and stuff like that, it leads to give us a spectra, and these things here is called the spectral line, right? So let me just remove all this so that we can write it easily. And okay, so this thing here, these lines are called the spectral lines, okay. So these are called the spectral lines, and these spectral lines depend upon the absorption and the emission spectra, as well as it depend upon the particular transition in the atom that we are using. And in this case we are discussing about a single hydrogen atom. Are we discussing about a single hydrogen atom? Yes, we are discussing about a single hydrogen atom. So like we have this atom, and we have like this is another energy level, this one is another energy level, and this one is another energy level, and the electron which is here, is jumping from here to here, so it is releasing some energy, and this is the case of the hydrogen atom. Now what if I have number of hydrogen atoms like these here? Like I have an hydrogen atom here, I have an hydrogen atom here, I have an hydrogen atom here, and all of them are being brought down by some kind of light, right? Some sodium light or some monochromatic light, and thus these electrons are this electron here, this one is absorbing energy, it is getting excited, it is moving in this direction, and thus every other atom in there is like transmitting to another energy level. So what will happen now, like there will be different spectral lines, right? If we go back, then this is for one hydrogen atom. So what will happen is, like there will be different spectral lines here of different colors, right? Like it will be a messy kind of a thing, but what if we can find here, is the number of spectral lines, right? So let us suppose that if there are n atoms in the sample that we have, so we have n atoms in the sample, right? And we have to choose two energy levels among them. So we have to choose two energy levels, right? So for choosing, if you have done this thing, I don't know if you have done this thing or not, and for choosing we always use combinatorics, and that we can say that it is NC2. So out of those n atoms we are choosing two energy levels so that we can calculate one spectral line, and thus we have from here n into n minus 1 by 2, right? So n into n minus 1 by 2 is the number of spectral lines. So if you don't know NC2, you can assume here that we have n atoms like these. So these are n atoms, right? And we have to choose any two of them. So for the first way we can choose it in n times, and in the second way we can choose n minus 1 times. But since they are not distinct, so we have to divide it by 2 because we are taking the case twice. Therefore we end up at n into n minus 1 by 2. So this is basically all about the spectra, or what is the spectra, why has the spectra come, what is the need for deriving the spectra. Like without this spectra we can do nothing. Like we could not have derived, couldn't have guessed like atoms have existed, right? Obviously Albert Einstein had to give existence of atoms, but this was way before this, right? To give the people a thought that you need to study about atoms because atoms exist, and he gave it using a brilliant usage of Brownian motion. And you can read that paper, you just Google search it, like Albert Einstein paper on the existence of atoms, Brownian motion, and blah 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 blah, and you'll get that paper. You need to read that paper, like it's one of the brilliant papers that is having. So that's it. It's about the absorption spectra, and the future videos we'll discuss about the limitations of the Bohr's model of atom, and what all came to existence when the Bohr's model of atom was came forward. Okay.